Hello everyone! Here is my presentation on Module 2 of OCR A-Level Physics.
Wait, you're really going to make a whole presentation on only Mod 2?
Yeah, what of it?
Dude, that's so lame.
Get the hell out of here!
Wait, no! Hello?
Quantities. What are they? Simply put, a physical quantity is a property of an object that can be measured. Sometimes, these quantities are just numbers and are dimensionless. For example, the number of apples in a bag, the number of radians in an angle, maybe? However, most of the time in physics, we measure things with units. This is because different units can refer to the same quantity but in different ways. For example, take a look at the meter and the foot.
Howdy, partner.
Nobody asked.
These units are both used to measure length, however, one of them is longer than the other.
And you're looking at it.
Oh, shut up, will you?
For this reason, scientists have agreed to use a common system of measurement worldwide so that these units can be easily compared across the globe. This system of measurement is known as the International System of Units, or SI for short, and feet just so happens to not be part of this system of measurement.
Ha! That's why I'm better than you.
Wait, what? I'm very popular in America.
Too bad. Sorry, but you're gonna have to go.
Wait, don't I have a... Hey, where the hell am I?
SI is composed of 7 base units. The kilogram,
Hey guys,
the meter,
That's me.
the second,
it's showtime.
the amp,
Sup?
the Kelvin, I'm Kelvin, the mole,
Hi.
and finally, the candela.
Hi, I'm Candela. I'm used to measure luminous intensity.
Wait a minute. Candelas aren't even part of the OCR A-Level specification. Bye-bye.
Wait, what?
How are you?
Not bad, thank you for asking.
Now let's talk about prefixes. Let's say your school bag weighs 1 kilogram. Alright, fair enough. How about 67 kilograms? Still pretty reasonable. What about 1 billion kilograms? Okay, now this is getting out of hand. The solution? Prefixes. Prefixes are used to denote multiples and fractions of units, because scientists hate using large numbers. For example, 1 kilometer is 1,000 meters, 1 milliamp is 1,000th of an amp, 1 gram is 1,000th of a kilogram.
Wait, what? What I don't have a prefix. What gives?
Yeah, I don't know about that one. That's a good question. The prefixes used in SI are...
Quecto, ronto, yocto, zecto, atto, femto, pico, nano, micro, milli.
Kilo,
Mega, giga, tera, peta, exa, zeta, iota,
Rona, and Quetta. Hang on, some of you guys aren't even part of the specification.
Here we go again!
Goodbye, cruel world.
Wow, a whole crowd this time.
Hey, Bagelnine. You forgot about us.
What are you talking about?
We're also part of specification. Yet you didn't think to include us. Yeah, what he said.
Ah, interesting. And what do you multiply your units by exactly?
I divide my units by 10. And I divide my units by 100.
Alright. Welcome aboard.
Yay!
What about us? You gonna include us too?
No, go away!
Well, that was rude.
You can say that again.
Alright, now that that's out of the way, let's look at some derived units. A derived unit is essentially a unit of measurement that is composed of the 7 base units, or at least the 6 that we need for the specification. Examples of these are meters per second, meters squared, coulombs, meters per second squared.
Bagelnine,
Yeah?
I don't think I'm a derived unit.
Why not?
I'm pretty sure I'm not composed of them SI units you were talking about. Because, like, I've got my own name, and I've got my own symbol, and...
Oh yeah, I should have mentioned this sooner. Some derived units have their own special names, but that doesn't necessarily mean they're their own base unit, you know?
Oh, I see. Well, in that case, What do you think I'm made up of?
Why don't we find out?
Wait, you don't have to...
Ow, that really hurt. Now I'm an amp and a second.
That makes sense, since current is the rate of charge flow over time. This gives us an equation, I equals to delta Q over delta T. We can do a bit of rearranging and realize that charge is current multiplied by time.
Why couldn't you just do that then? Why do you have to cut us up like that?
Too bad. Anyways, the Coulomb isn't the only derived unit with a special name. Others include the volt, the joule, the hertz, the watt, the newton, the ohm, and many more.
Oh god, he's gonna chop us into our base units too, isn't he?
No, I wasn't going to.
Phew, that's a relief.
But now that you mention it...
Everyone run for your life!
Program me a square per second cube did we ever do to you to deserve treatment like this?
Last but not least, let's try to understand how scalars and vectors work. The thing that scalar quantities have in common with vector quantities is that they both have a magnitude. However, unlike scalars, vectors also have a direction, making calculations with them pretty tricky. Examples of scalar quantities are temperature, luminous intensity, speed, distance, and current.
But don't I turn negative when you flip the...
Well, yes, but you don't obey the rules of vector addition.
Oh, okay.
Examples of vector quantities are force, momentum, acceleration, velocity, and displacement.
Wait, did you just say our names again?
Yeah?
Why?
Well, distance is the scalar magnitude of displacement, and speed is the scalar magnitude of velocity.
Oh, okay.
Now let's look at an example of calculations with vectors. Suppose we have a vector named Andy.
Hi, I'm Andy.
Andy has a magnitude of 6 newtons and is at a bearing of 30 degrees. Let's try to find the horizontal force, Beth.
I want to know too.
Using trigonometry, we can multiply Andy's magnitude by the sine of his bearing. This tells us that Beth is 3 newtons due east. Now let's get rid of Andy.
Wait, what?
What are you?
I'm a vector. You?
I'm a prefix.
Cool.
What did you do with Andy?
Forget about that guy. He's in a better place right now.
You killed him?
No, I just sent him to a room of useless crap.
Oh, okay.
Anyways, let's suppose we have a new vector named Charlie.
Hi there.
Charlie has a magnitude of 5 newtons and is also at a bearing of 30 degrees. Let's find the resultant force, Dennis.
What's up?
First, let's arrange these vectors tip to tail. What we've constructed is a vector triangle, and the angle between Beth and Charlie is 120 degrees. This is because Charlie's bearing was 30 degrees, but there's an extra 90 degrees between Beth and Charlie, so the total angle is 120 degrees. Now we can use the cosine rule to find the magnitude of Dennis, but to save time, I won't actually go through this process.
Oh, come on. How am I supposed to be certain of my magnitude now?
Too bad. Anyways, your magnitude is 7 newtons.
Okay, cool. But what about my direction?
Well, to figure that out, we can use the sine rule. Again, I'm not going to waste my time doing these calculations in the video.
Oh, come on.
But the angle between Charlie and Dennis should be about 38.2 degrees.
Okay, and what would that be as a bearing?
Okay, to find your direction as a bearing, we simply subtract the angle we found from 90 degrees, which should be about 52 degrees. There, happy now?
Absolutely.
Good. So in conclusion, SI is the globally accepted measuring system for measuring quantities. The 7 base units, 6 of which you need for A-level, can be combined to form the derived units. These units can also have their own prefixes, which can multiply or divide the quantity by a power of 10. Quantities can also be scalars and vectors. All quantities have magnitudes, but vector quantities also come with a direction. So thank you all for watching this glorious presentation. I hope you enjoyed it. Nope.